Hey guys, welcome to Recitation 15.4. So today we will solve problems involving limits, series and their integrals. So basically we will see how we can swap the integral with the series, but also how we can pass through the limit inside the integral. All right, so let's get started. So the American Mathematical Monthly back in 2006. And the problem has the following statement. So basically, we find the limit as n approaches infinity of 1 over n times the integral from 0 to n of x times natural log of 1 plus x over n, everything over 1 plus x dx. All right, so that's the first problem. Well, if you look at it, and in fact, I will show you even a more general approach to this one. So let's say the solution one, first solution, let's say more elementary. Basically, we would like to work inside the integral a bit. But first, we would like to perform a change of variable, so a U substitution. So using the substitution x over n equals t. Well, this means that our integral, in fact, let me denote the integral. So first denote my integral 1 by in. Now we use this substitution, right? X over n equals t. So we change the variable, and our integral will become the following. So we will have that in is the integral from 0 to 1 of this guy here. So x will be nt. So this would be and it will be nt times log of 1 plus t, everything over 1 plus nt dt. So and 1 over n will go right. All right, so basically I have this one here. All right, let's put it here. Okay, so that's the integral I'm dealing with. And now I have to find the limit of this one. And what I'm going to do, I'm just going to do a trick here. So an elementary trick. So now this in, which is the integral from 0 to 1 of, so I'm going to just add and subtract 1. Okay, so basically, and now by doing the elementary operations with integrals, so this would be nothing else than just the integral from 0 to 1 of log of 1 plus t dt, which is, this one is basically computable. And now let's be careful here, minus the integral from 0 to 1 of log of 1 plus t, everything over 1 plus nt. Let me move this a bit. So this is, all right. The first one, if you look at the first one here, so this integral here can be computed. And I will do it, I will leave this to you. So just by doing some integration by parts, and I'll leave this to you as an exercise, that we don't lose precious time, the trivial stuff. Integration by parts, this will give us 2 ln of 2 minus 1. All right, but now we need to take care of this one here, right? So once we take care of this one, so let's do that. So now the main goal is to find the limit of this one. So we need to find the limit as n approaches infinity of this guy here, the integral from 0 to 1 of log of 1 plus t over 1 plus nt dt. All right, so well, we need to do a bunch of stuff. As you can see, we have an and there, so maybe we'll do some kind of a squeeze theorem. In fact, we will prove that this limit is actually 0. So in fact, we prove that this limit, so the limit as n approaches infinity of this integral is in fact 0. Okay, so we're going to use a squeeze theorem. So basically we have that 0 is less than the integral from 0 to 1 of log of 1 plus t over 1 plus nt dt. And now what I'm going to do, I'm just going to neglect this one here. So I'm going to just do a brutal estimate. So this will be less than this integral from log of 1 plus t over nt dt. So if you want, this is nothing else than just this integral. And I think we've come across this integral a couple of times. This is we have seen in the lecture 15.3 or 15.4 lecture. I don't know, I don't recall exactly. This has a value, so it's pi squared over 12. And from the squeeze theorem, we have a factor n over n. As n approaches infinity, this goes to 0, and this goes to 0 as well. So basically, this will go to 0 by the squeeze theorem. So again, indeed, this is 0. And now finally, the limit as n approaches infinity of my integral en is nothing other than just 2 log 2 minus 1. And that's it. So that's the first solution, which is more elementary. But also, well, suppose if you did not have this idea of doing this trick here by adding 1 and subtracting 1, right? So, right, see, starting from here, maybe if you would look only at this part here, right? Maybe you could have done it differently. And indeed, if you look at this, maybe I'll just sketch the solution. I won't go into many details. So let's see, solution number 2. So we look at the integral. After we've done the u substitution, so we look at this integral. So it's the integral from 0 to 1 of nt natural log of 1 plus t over 1 plus nt dt. Okay, and what I'm going to do is I'm just going to denote this sequence of functions. So let fn given by fn of t is n of t. Okay, let me put log of 1 plus t there as well. 1 plus nt. Okay, this is a sequence. It's a monotonic sequence. It's an increasing sequence of functions. So once you know this, of course, they're continuous. You don't have any problems. So you can use the idea is to use the monotone convergence theorem. So basically, you can pass to the limit inside as n approaches infinity. So by the monotone convergence theorem, so these are some details here, right? So I think this sequence is monotonic anyway, increasing, decreasing, monotone. So by the monotone convergence theorem, we have that the limit of the integral is nothing else than, so it's the limit as n approaches infinity of this guy here. And now we can swap the limit with the integral. So basically this would be nothing else than just the integral of the limit as n approaches infinity of this guy here, of fn. Well, pretty clearly, this is nothing else than just the integral from 0 to 1 of log of 1 plus t. And again, dt, this is just a simple introduction, integration by parts. So this would be 2 log 2 minus 1, and that's it. All right. So you can use some fancy stuff as well to be more powerful. You see, sometimes you don't see the trick with adding 1, subtracting 1, then do this squeeze theorem, you know, that's a little bit tricky. So you can do it in this direct way. But there is a more general phenomenon here that I'd like to show you. There is, in fact, we can prove something more general. So let me put here solution number 3 if you want. We prove a much general statement. And this statement is the following. So instead of this problem, will just follow immediately from as a particular case from that from the following statement. Let's call this a lemma. In fact, I think it was a Romanian math Olympiad back in the day. I think so. 2003. Basically, the problem says the following. So let f define on the it's a real value defined on negatives, and g, say function from 0, 1 to r. So these are continuous functions. Both of them are continuous functions. And we know that such that the limit as x approaches infinity of f of x is L. Okay, and this L is actually a real number. Then show that you have the following statement. In fact, let me write it in this way. So the limit as n approaches infinity of 1 over n times the integral from 0 to n of f of x times g of x over n dx is L times the integral from 0 to 1 of g of x dx. Okay, so you see we have a much more general statement that we prove. And in fact, our problem follows immediately from this general statement. So let me point out a remark first. our problem is just a particular case for, let's say, f of x is what? In our case, f of x is x over x plus 1, and g of x is nothing else than just log of 1 plus x. Well, the limit as x approaches infinity of f of x is 1, so it's just the integral from 0 to 1 of g of x, which is the integral from 0 to 1 of log of 1 plus x, which we already computed. So it's 2 log 2 minus 1. All right, so it follows immediately. All right, let's prove this lemma. All right. So the proof of this lemma, in fact, it will be very, very instructive. It's a very nice proof. So you see, we're going to do a trick here. So first, let's look at this this integral, right? So first, we look at the integral so I'm going to look at the first integral. So 1 over n times the integral from 0 to n of f of x times g of x over n dx. So this guy, if we look at this, so what I'm going to do is I'm just going to add and subtract an L inside here. So I'm going to write it in this way. So it's 1 over n times the integral from 0 to n of f of x minus L plus L times g of x over n dx. And this will give us, so let's do the computations here. So basically this would be 1 over n we're going to have something like this. Okay. So let's take, so wait, sorry, let's take here. All right. So for the first integral, after a change of variables, this was nothing else than just the integral is L times the integral from 0 to 1 of g of u du. Right. Let's say we do use this substitution. Okay. So this would be nothing else. Let me just write it again. So it's 1 over n times the integral from 0 to n of f of x minus L and g of x over n dx plus L times the integral from 0 to 1 of g of u du. Now, we need to take care of this guy. So this is the guy we need to take care of. So basically, we're going to use pretty much the same idea as we have done in the particular case. So basically, we'll try to squeeze this integral. In other words, we will prove that we show that the limit as it then approaches infinity of 1 over n times the integral from 0 to n of f of x minus L times g of x over n dx is 0. So if we're done, if we show this, then the problem is over. All right. So now we know that since that the function g is a continuous on a compact interval, so basically it's bounded. Since g is continuous on a compact interval, it follows that g is bounded And this implies that if we look at this integral, right? Right, if we, well, so this means that this will be less or equal than 1 over n times, so g is bounded, so we're going to have a constant m times the integral from 0 to n of f of x minus L dx. In other words, this would be, if we apply the triangle inequality, this would be less or equal than m over n times, or let me put it this way, maybe so that we can see it better. It's m times the integral from 0 to n of the absolute value of f of x minus L dx. So here we apply the triangle inequality, right? Okay. So now we need to take care of this guy. So if we show that this guy here, so if we show that this guy goes to 0 or then approaches infinity, we're done. All right. But we will use the Cezar-Stokes lemma. So by the Cezar-Stokes lemma, so the discrete version of the L'Hopital rule, we have that the limit of this guy here, so the limit as n approaches infinity of this integral is the limit as n approaches infinity of this guy here. So, okay, so this is nothing else than just the limit as n approaches infinity of the integral from n to n plus 1, where here I use the additivity of the integral of the absolute value of f of x minus L dx over 1, right? Or if you want, let me write it again, although it's a bit redundant, but anyway, let's do it. So we'll end up with this. But now, what are we going to do? Now is just like we're going to apply the mean value theorem. So by the mean value theorem for integrals, MVT, let me put here for integrals. So the first mean value theorem, in other words, first mean value theorem, we have, it follows that this integral from n to n plus 1 of f of x minus L dx, this is nothing else than just this guy here. F of Cn minus L for some Cn in n plus 1. All right, that's beautiful. So basically, this is nothing else than just the absolute value of f of Cn minus L, an absolute value, right? But now we know that, but since the limit is x approaches infinity of f of x is L, and since the limit as n approaches infinity of Cn is infinity, it follows that the limit as n approaches infinity of f of Cn minus L in absolute value is 0. All right, that's great. So basically, this guy is 0. Now we go back and by the squeeze theorem. So by the squeeze theorem, the conclusion follows. Okay, so that was the generalization of our problem. You see, you have three ways of dealing with the first problem. So this generalization is a very, very nice, nice problem because it has pretty much everything in it. So has like pretty much everything. Mean values theorem, even Cezar-Stolz lemma, squeeze theorem, triangle inequalities, you name it. All right, so that's the first problem that I want to discuss. So I have a bunch of other problems. So the second one, this was a Putnam problem as well. So this was, I would say, okay, let me just, so this was a Putnam A3 2011. The problem states, I'm just gonna put the statement as it was given in the contest. So find a real number C and a positive number L for which the limit as R approaches infinity of R to the power C times the integral from 0 to pi over 2 times x dr times sine of C, sine of x dx, everything over the integral from 0 to pi over 2. This time we have x dr times cosine of x dx, such that this guy is L. All right. All right, so this problem, I mean, if you look at it, maybe you'll observe something. Well, usually the official solution uses some kind of a Taylor series expansions of sine of x, and of course you can integrate by parts on the bottom, and then you will do some kind of a squeeze theorem, stuff like that. But in fact, there is a much more general phenomenon that's hidden behind this problem. In fact, the first moment when I saw it, basically it just came to my mind immediately that we have the following lemma, which I already discussed in one of the lectures, I think 15.3, 15.4, I don't recall exactly. So recall the lemma, the following result. Let's call this lemma. And I'm gonna just recall it as a general as possible. So basically, let me consider f, define on 0, 1, real value. So I'm gonna consider this to be an integrable function. Which is continuous only at 1. Then we have the following. The limit as n approaches infinity of the integral from 0 to 1 of x to the n times f of x. Obviously, this is 0. But also, and we have something even more, a little bit more interesting, which we prove. The limit as n approaches infinity of n times this integral is f of 1. We proved this result. So it was proved in one of the lectures. Okay? Well, you can actually, you see, this is the most general statements that you can see, but the same result will hold true if f is a C1 function. well, when f is, well, of course, the first part is trivial. You don't need, you just need continuity. You know that f is bounded, and then you can just use a squeeze term, so there will be no problem with that. The problem is the second one, because you have to split the integrals from 0 to some epsilon, and then from epsilon to 1. And then you have to look at, or you can do it just like we did it in one the lecture. We're using the Lebesgue-dominated convergence theorem. Okay, but like I said, in the case of when f is a C1 function, you have much more freedom, because you can use integration by parts, for example. You can bound it. You can use the squeeze theorem, so you don't have any problems. Anyway, I'll leave that as an exercise for you to show that, or that this is true for C1 when f is a C1, right? So it's a differentiable with the derivative. The first derivative being is a continuous function. All right. So you see, in our case, in the particular case, we have the sine and cosine. So these are C1 functions, so you don't have any problem. So you can prove the lemma in its weaker version. All right, let's use it just like this, right? So you see, I have the integral from 0 to pi over 2. So I need to have the integral from 0 to 1, no problem. We can do the substitution. So with the substitution, x equals pi over 2 times t. Our expression becomes the following. So let's see, what does, so this will become, so r to the power c plus 1 times, and now let's look at this fraction. Let's be careful here. So here I have r times the integral from 0 to 1 of t to the power r times sine of pi over 2t dt. And on the bottom, we have r squared times the integral from 0 to 1 of t to the r times cosine of pi over 2t dt. Okay, so this is what our expression, and we have to take the limit of this, keep that in mind. So now, by the above lemma, you see that the top looks very nice. See, look at this. The top looks very nice. So by the above lemma, we have that the limit as r approaches infinity of r times the integral from 0 to 1 of t to the r times sine of pi over 2 times t dt. So this is nothing else than just, so f of 1, so it's sine of pi over 2, just 1. All right, great. But you see on the bottom, if we look, it doesn't look the same. So we need to do something. Well, what can we do? Well, maybe we can do some integration by parts. You see, we have r squared there. So maybe we do some integration by parts. So next, integrating by parts. We have, let's see. So let's see. So we have that r squared times this integral from 0 to 1 of t to the r times cosine of pi over 2 t dt. So this guy is, so that will be t to the power, so it's r squared over r plus 1 times the integral from 0 to 1. Okay, let me write it in this way, cosine of pi over 2t, and we'll have the derivative of t r plus 1. All right, great. So this would be, let's be careful here, r squared over r plus 1 times t to the power r plus 1 times cosine of pi over 2t from 0 to 1. Okay, let me write it again. This is r squared over r plus 1 times t to the power r plus 1 cosine of pi over 2 times t, everything from 0 to 1. All right, minus r squared over r plus 1 times the integral from 0 to 1 of t to the power r plus 1 cosine of pi over 2 times t dt. Right, I hope I didn't do any mistakes. So let's keep going. So this mess here, so that will be for Cezar. So this would be, so okay, so 1/2 times cosine of pi over 2. So, okay, so this would be pi over 2 times r squared over r plus 1 squared. Okay, let me write it in this way. Times here we'll have sine of pi over 2 times t. Okay, dt. And now we're going to use the lemma again. You see, we have this part here. So this by the lemma will converge as n approaches infinity at what am I writing here? This cosine. It's cosine here. So this would be, so here we apply the lemma. Okay, let me just write it. We apply the lemma. So now, all this together combined will give us, so this will imply that the limit as r approaches infinity of r squared times integral from 0 to pi over 2 times t to the r times cosine of pi over 2 times t dt. This is nothing else than just pi over 2 times the limit as n r approaches infinity of r squared over r plus 1, everything squared, times sine of pi over 2, because this, in fact, here I have sine. What am I talking about? Anyways, so this would be nothing else than just pi over 2. So therefore, at this point, clearly, C is -1, and L is 2 over pi, and we're done. Anyway, so the problem is fairly easy if you know the lemma. Okay, now there's another problem. Now let me do a problem with a series where you have to prove an integral version, and this again was a Putnam problem, so problem 3. So this was a Putnam A4 1969. I did something very similar, almost an identical problem I did at one of the lectures. Okay, so the problem says the following: show that this integral, the integral from 0 to 1 of x to the power x dx, this is nothing else than just this series. Times n to the power negative. This was a Putnam A4 1969. So we will proceed in the same way as we proceed for the other problem. So basically, we would like to rewrite this integral. So we write this integral in the following way. We're going to use the exponential function here. So it's e to the power ln of x dx, which is, all right, great. So I'm going to write it in this way. But we know that the power series expansion, that e to the y is of the exponential has, right, for we have this power series expansion. All right, great. So e to the x log of x is this sum. All right, so we have this. So we need to make, and I'll leave this to you as an exercise. This is uniformly convergent. I'll leave this to you as an exercise. So show that this series is uniformly convergent. All right, that's great. That's exactly the information we needed. So this means that this integral that we started with, which is the integral from x dx, and we ended up with this integral. This is nothing else than just the integral from 0 to 1 of the sum of this series. So this series of functions is, we said, is uniformly convergent. So we can swap the sum with the integral. So this would be nothing else than, so here we use the fact that it's uniformly convergent. So this would be nothing else than just the sum of, let's put here 1 over n factorial times the integral from 0 to 1 of x ln of x to the power n dx. So basically now we need to take care of this integral. Right. Anyway, this integral, actually we've done this before, and we can relate it to the gamma function. So, so this integral 0 to 1 of x to the n times log of x. So if we do, let's see, so if we perform the substitution, let's say x equals e to the u. So this would be that this integral will become nothing else than just the integral from x is 0, u is negative infinity, and when x is 1, e is 0, so e to the n u times u to the n, and dx is eu du. So basically, this is nothing else than just this integral, e to the power n plus 1 u to the power n du. All right, great. So now this started to look more like the gamma function. So now I'm going to do another substitution. Let's make so another substitution is, let's say, n plus 1 u equals negative v. So I'm going to do this a bit because I want to emphasize the gamma function. You will see immediately what do I mean by that. So this means that so another substitution will which gives us so this will give us the following. So this integral from negative infinity to infinity, u to the n du. So after this substitution, this will give us, let's be careful here, the integral from infinity to 0. Yes, of e to the negative b times negative v to the power n times 1 over n plus 1 to the power n. And now let's be careful here. Du negative dv. It's negative dv. Or if you want, is the integral from 0 to infinity of e to the negative v times negative 1 to the power n, p to the n, at 1 over n plus 1 to the power n dv. All right, so that's the integral. Okay, so we have a factor here. So this would be 1 over n plus 1 to the power n times this integral. 0, okay, negative 1 to the power n times this integral e to the negative v times v to the n dv. This is nothing else. If you look at this, now you can recognize that that the gamma, Euler's gamma function, gamma of n, right? So this is the Euler gamma function. Sorry, gamma of n plus 1, which is n factorial. This is the Euler gamma function. Anyway, I think it's pretty clear from now that this implies that we look at this. Finally, this series is nothing else than just this one. I forgot somewhere negative. Okay, n factorial. Right. So this should be. Why did I forget the n to the n? Ah, okay. So I forgot it here. -1 to the power. Okay. Yes. Yes. Okay. All right. So if we sum up from n equals 1, so basically that's exactly what we have. So -1 to the power n plus 1 times n to the negative n. All right. So that's the problem. So that's anyways pretty much similar. And now let's move to another problem that I have in mind. This again, it's a famous problem. It's pretty well known. As the following. So this is problem number. What was it? This is problem number 4. And this was a Putnam B3, 1967. In fact, it's a very famous problem at this point. You can find it in a Berkeley book. It's a preliminary exam problem as well. So in fact, it was proven, it's a kind of a property of the Fourier coefficients of an integrable function. It was proven in a much more general setting. But anyway, let me state it. So the problem says that I have f and g be defined on reals and real values, continuous functions. So be continuous functions. Such that f is periodic of period 1. So basically f of x plus 1 is f of x. And let's take also g to be periodic, although it doesn't really matter that much. I don't necessarily need that for all real x. And you will see from the proof for all real x. Prove that you have the following. That the limit as n approaches infinity of the integral from 0 to 1 of f of x times g of nx, g of nx dx is the integral from f of x times the integral from g of x. All right, so like I said, this looks like a property of the Fourier coefficients of an integrable function. And usually the classical solution using some Stone-Weierstrass approximation by trigonometric functions, by a combination of sine and cosine. So, but I would like to show you like a more elementary solution. And first, there are plenty of solutions to this one, but I'm going to show you my favorite one. So first, let's prove the lemma. So basically, this lemma says that suppose that we have a continuous function, a continuous and periodic function. So suppose h is a continuous and periodic of period 1. Of period 1. Okay, then we have that, and actually that's not very hard to see, that the integral from a to a plus 1 of h of x dx is the same as the integral from 0 to 1 of h of x dx. All right, so first let's prove this lemma. The proof of the lemma, pretty straightforward, is nothing else than just an application of the fundamental theorem of calculus, and I'll just prove it immediately. So basically, if we take this function, so let h of a is the integral from a to a plus 1 of h of x dx. So basically, by the fundamental theorem of calculus, we know that h prime of a is the same as h of a plus 1 minus h of 0, h of a, sorry, which is 0, right? We take the derivative of this, we know that, because that is 0, since we know that because of the function is periodic of period 1. All right, great. So this means that the function, the h is a constant. So basically, in particular, h of a is h of 0. In other words, this means that integral from a to a plus 1, so we know who h of a is. So this is nothing else than the integral to 1 of h of x dx. All right, so that's the proof of the lemma. So, and now let's see how we're going to use this lemma to prove our problem. So now let's go back to our problem. So what we're going to do is just gonna, if we look at this guy, we're gonna look at this guy a bit. And we're gonna split this integral into n sub integrals. So according to the division, so equidistant bounds. So basically, we're going to write it in this way. So write the integral from 0 to 1 of f of x times g of nx dx. We're going to write it in this way. So we're going to split it like this. So this will be the sum of the integral of k minus 1 over n to k over n of f of x times g of x, g of nx dx. Okay. Now, without loss of generality, let's assume that g is actually non-negative. So we can assume that. So without loss of generality, assume that g is positive. Otherwise, we're going to add a constant, no problem. So x in 0, 1. Okay. So now what we're going to do, I'm gonna look at this particular integral. So let's see, and we can apply the second mean value theorem for integrals. So by the second mean value theorem for integrals, so this will give us, we have that this integral from a minus 1 over n to k over n of f of x times g of nx dx. So this guy is nothing else than just f of ck over this integral. All right, for some ck in okay, great. Now let's look at this. Now we're going to look even further. We're going to look at this integral here. So let's do a change of variables. So moreover, this integral that you see here. So after a substitution, let's say nx equals u. Okay, so this will give us nothing else than just 1 over n of the integral from k minus 1 to k of g of u du. Beautiful. But now, if we go even further, this will be nothing else by using the lemma. There's nothing else than just 1 over n times the integral from 0 to 1 of g of u du. All right, beautiful. Basically now, this means that, so finally, the integral from 0 to 1 of f of x times g of nx dx is nothing other than just so. And this guy here, if you look at this, this is 1 over n as f of ck times, of course, I'll forget this sum here. Times the integral from 0 to 1 of g of u. Let's change the variable g of t dt. Anyway, it doesn't really matter. For some ck in this interval. All right, so there's one last step now we need to do. So now if we take the limit, since the limit as n approaches infinity, this is basically a Riemann sum. F of t dt, the conclusion follows. So that's it. And that's the end of the problem. In fact, anyway, maybe I shouldn't go over this, but this was proven in a much more general setting for measurable functions, so complex value measurable functions. In fact, there is a paper of Luxembourg in 1962, published in the American Mathematical Monthly. In fact, it's called exactly like this, a property of the Fourier coefficients of an integrable function. So it's published in 1962. I think you can find it on the internet. All right, guys, I think I'm going to stop here. So basically, this sums up everything about single variable integration. So starting next time, I will do multivariable calculus, both lectures and recitations. All right. Bye-bye.